Hello, welcome back to the section on linear regression. In the previous video, we talked about the criteria to help us find the best linear model to fit a set of data. It was called least squares regression, where we wanted to minimize the sum of the squared error. And so now we want to do a simple example to see that in action. So here we have some data, 6 data points. Here they are plotted, and we just want to find the best fit line for it. So let's try to do it by hand first, and then we'll compare that to what our regression line will say is the optimal fit. So before I show them what I would do, I encourage you pause the video and try your best fit line and see how close you can get to reality. All right, so I'm just going to take a ruler and eyeball it. Of course, it's not a perfect fit, so there's lots of possibilities. But for me, I think I'm going to do something, maybe something like this. So we need to find the equation of this line. We know it has an intercept here of about 2. And then the slope, we just need to find another point that it passes through. Looks like it passes through this point. That is 8, 11. And so since it also passed through 0, 2, then it looks like that would be about 9/8. Because the rise over the run, the rise is about 9, the run is about 8. So 9/8 x. Okay, so let's see how that compares to the actual best fit line. So here's our same data set with it plotted. So let's go ahead and put our model up here. And remember we said it was 2 plus 9 divided by 8 times the x value. We can drag that down. And if we want to see how that compares, we can insert a scatter plot. And if we want to see this more as like a line, I'll change the series chart type. Make that a smooth line. And so there's our plot. Now, how good of a job is it? Well, remember one way of analyzing that is to look at the squared error and then add it up. So let's go ahead and do that. So squared error, I'm just going to call SE. So SE is equal to the model minus the actual is squared. Drag that down. And so SSE is going to be the sum of all those numbers. So the sum of all those numbers is 36.25. So one downside of SSE is that there's no context for it. For some problems, 36 may be a great value, and other problems, 36 could be terrible. So by itself, that doesn't tell us much. The other thing to be aware of is that the units of this is actually the square of whatever the units of our y values are. So we can't even really make sense of units. One way to get around that is to square root it. So then that gets our units back. The other thing we could do is we could take the mean squared error instead of the sum of the squared error. And then we could have a little better understanding of that number in that sense. But if our goal is to just find the best model, it doesn't matter whether we square root or take the mean. SSE is as good as anything, and so we'll focus on that. All right, so how do we find the best model? So remember we had a formula for the values for M and B. And as you may recall from that formula, we needed to know the product of the x and yi's and the xi's squared. So I'm going to write product here. And I'm going to do xi times yi. And drag that down. And then xi squared. And that's just going to be this number squared, and then drag that down. And we want the sum of those as well. So this is the product sum, and this is the x squared sum. And then we had a formula for the m and the b. Remember, it wasn't pretty, but we can do it. So remember, it was n. Our n was, we have 6 data points. So it's 6 times this product sum minus, oh, I need a few other sums here. Let me come back to that. All right, so notice this is the sum of the xi's, and this is the sum of the yi's. All right, so now we can do our formula. So 6 times the product sum minus the sum of the xi's times the sum of the yi's. And that's my entire numerator of m, so I'll put that in parentheses. And then I'll divide by the denominator, which is again 6 times the sum of the squares minus the sum of the x's, that quantity squared. So that's our value for m. And then we can do the same thing for b. It's the sum of the yi's minus whatever we found for m times the sum of the xi's divided by 6, since we have 6 data points. All right, so let's see how we did. So the least squares model. So that's going to be m times our x value plus our b value. Again, we don't need all these decimal places. We need to put dollar signs around the 12 and the 13. All right, and let's take a look at our plot. Again, we'll change these to lines for comparison's sake. So, not a huge difference in terms of the model, okay? So again, just by eyeballing, it would be hard to say which one's better, but if we are in agreement that the least squares criteria is the way to go, then we can actually quantify if it's better. So once again, I'm going to find the squared error by taking our model value minus the actual value and then squaring it. We certainly don't need that many decimal places. Drag that down. And sure enough, we get 33.2, which is definitely less than 36.25. All right, and so that is apparently the best possible SSE we can find. Now, this is just kind of verifying how these formulas work and that it can be done by hand. So let's say I wanted to have Excel do this calculation for us because we don't want to do all these calculations by hand if we can avoid it. I can just select the data, insert a scatter plot. Okay. And then I can add a trend line, make sure it's linear, make sure I can see the equation. And sure enough, Excel gets the exact same thing we do. So that could be the end of the story, but you might ask yourself, is this really the best line? Because we've got this one point that kind of throws a wrench into having a nice fit. And that shows itself when we look at the SSE. Even for our best model, our SSE is heavily influenced by one point. And that can be a problem because if that one data point is somehow based on error, either data collection error, measurement error, something else that's going on that we hadn't really considered, then that can highly affect our model, even though it shouldn't really be in there. So it's known as an outlier, and we have to decide, is it an outlier that should be included or not included in the rest of our data set when we're making our model. Now, just because it makes your model worse is not a reason to discard it. So you can't just use that criteria. You have to have some reason to believe that this data point was the result of something erroneous. Again, if someone, let's say they're putting in their height and weight, and they put their height and weight in kilograms and centimeters instead of inches and pounds, then you could get a point that is clearly not in line with everything else. That would be a time to disregard it. But if it just doesn't fit the data, you have to leave it. Just to illustrate the point of how much the data changes, notice we can delete this one point, and notice two things happen. One, the slope and the intercept change dramatically. The squared error changes dramatically. And the fit, just overall visually, we can see is a lot better looking. So we would really want to analyze that data point before we proceeded on to the next step. So that's a simple example. There's more we can say about linear regression, and we'll catch that in the next video. So we'll see you there.